Hello friends, welcome back to my YouTube channel. This is part number 6 of my discussion on adsorption, and I will continue my discussion on adsorption isotherms. And today I will be talking about the Brunauer-Emmett-Teller, that is BET adsorption isotherm. In part number 5, that is in my previous video, I had discussed Langmuir adsorption isotherm. I am giving link to the entire playlist on adsorption in the description section. Those who have not yet seen my earlier videos, you please watch those videos. So let us start the discussion for this video. To begin with, let us know how adsorption equilibria is representation of the equilibrium. So, when the adsorbent phase, that is solid phase, comes in equilibrium with the fluid phase, 3 parameters are important at equilibrium. So, at equilibrium, 3 parameters are involved. Which are the 3 parameters? One is the concentration of the adsorbate in the fluid phase. We will denote it as Ca. And then the second parameter is the concentration of adsorbate on the surface of the adsorbent. We will call it as Cs. Then the temperature T. So these 3 parameters are important, or these 3 parameters are involved when the solid adsorbent phase comes to equilibrium on the fluid phase. So the case is you have the adsorbent and you are contacting this solid adsorbent phase with a fluid phase. It could be either a liquid solution or a gaseous mixture. Let us say that it is a gaseous mixture of 2 components, A and B. So this yellow molecules, these are A molecules, and the blue molecules, these are B molecules. So the adsorbent is contacted with the mixture of A and B. So I had said that the yellow molecules are of A and blue molecules are of B. Now this adsorbent, if it has an ability to preferentially concentrate A on its surface, some of A molecules will be going onto the surface. And then there will be a dynamic equilibrium. I have already discussed how dynamic equilibrium is reached in adsorption. So you please watch that video. So in this case, you have the fluid phase, and I'm saying that concentration of A in the fluid phase is Ca, whereas concentration of A on the surface of the adsorbent, it is Cs. So you have concentration in the fluid phase, you have concentration on the adsorbent surface, and there is one more parameter, which is temperature. So at equilibrium, you have these 3 parameters, and we are going to use these 3 parameters to represent the equilibrium. So let us understand. So I have already discussed all this in my previous video, so I am just summarizing the discussion. Then the capacity of a adsorbent to adsorb a particular component, it depends on the interaction between these 3 parameters, interaction between the above listed parameters. And in order to represent the equilibrium, what we can do, one of the above listed parameters is kept constant, while the other 2 are varied. So in order to represent the equilibrium in a proper way, in a simple way, what you can do, you can keep one parameter constant and vary the remaining 2 parameters. And in this way, you can represent the equilibria, adsorption equilibria. So accordingly, when you are doing this, that is when you are keeping one parameter constant and varying the other two, if you do that, there are three different ways in which you can represent the equilibria. How? The first way is you can plot Ca against Cs by keeping T constant. So one way is Ca could be plotted against Cs by keeping T constant, and the other way is Ca, it is plotted against T by keeping Cs constant, and the third way is Cs is plotted against T by keeping Ca constant. So these are the three different ways in which you can represent the adsorption equilibria. And this is possible when you are keeping one parameter constant. So you can keep temperature constant, you can keep concentration on the adsorbate surface constant, and you can keep concentration in the fluid phase constant. So in this way, you can represent the adsorption equilibria in three different ways. And when temperature is kept constant, the resulting curve is nothing but the adsorption isotherm. So you get adsorption isotherm when you plot Ca against Cs by keeping temperature constant. That's adsorption isotherm. Just a minute. So you get adsorption isotherm when you do this. When Ca is plotted against Cs by keeping T constant, what you get is adsorption isotherm. And we are talking about adsorption isotherm in this particular video. So let us move on. So as I said, adsorption isotherms, these are obtained by plotting Ca against Cs by keeping T constant. So you could be plotting Ca on the y-axis, Cs on the x-axis, and you could be getting a curve like this. And this curve is then called the adsorption isotherm. It is called the adsorption isotherm. The resulting curve, you call it as adsorption isotherm. So the resulting curve, as I said, is called the adsorption isotherm. And this is the commonest way of representing adsorption equilibria. Adsorption isotherm, it is the commonest way of representing adsorption equilibria. Different adsorbates will give different adsorption isotherms on the same adsorbent. I have talked about it in my previous videos. And similarly, the same adsorbate will give different adsorption isotherms on different adsorbents. So different adsorbates will give different adsorption isotherms on the same adsorbent, and the same adsorbate will give different adsorption isotherms on different adsorbents. Okay, so I hope this is clear to you. I have talked about this concept in my earlier videos. You please watch those videos. Let us move on. What are various adsorption isotherms? I have summarized them over here. The simplest adsorption isotherm, the first way is to use the simplest adsorption isotherm. And simplest adsorption isotherm is applicable to those cases where adsorption mechanism is very simple. But such simple systems are very rare. Very few systems are simple. Then, apart from the simplest adsorption isotherm, which is applicable only to simple cases, the commonly used adsorption isotherms, you have the Langmuir adsorption isotherm. I have discussed the simplest adsorption isotherm. I have discussed the Langmuir adsorption isotherm, and today I am discussing the Brunauer-Emmett-Teller, that is BET adsorption isotherm. So commonly used adsorption isotherms, you have the Langmuir adsorption isotherm, the Brunauer-Emmett-Teller, that is BET adsorption isotherm, and the Gibbs adsorption isotherm, the third one. Now, these three adsorption isotherms, these are based on various theories. So, the equations applicable, they are derived based on various theories that are available in the literature. But the problem is none of this is applicable universally. You cannot use any of these three adsorption isotherms universally. It could be applicable to selective adsorption cases. You cannot, none is applicable universally. And the other important thing to note for this adsorption isotherms is these adsorption isotherms, they are applicable to adsorption of gases. Then you have the Freundlich adsorption isotherm. This is not based on any adsorption theory. It is applicable to the adsorption of liquids. It is applicable over a small concentration range, and it is applicable to dilute solutions, applicable for dilute solutions. So the first three, the Langmuir adsorption isotherm, the Brunauer-Emmett-Teller, that is BET adsorption isotherm, the Gibbs adsorption isotherm, these are applicable to adsorption of gases. Whereas the Freundlich adsorption isotherm, it is applicable to the adsorption of liquids. It is not based on any adsorption theory. It is applicable over a small concentration range, and it is applicable only for dilute solutions. So, in this particular video, I am discussing the Brunauer-Emmett-Teller, that is BET adsorption isotherm. So, let us move ahead. So, let us talk more about the BET, Brunauer-Emmett-Teller adsorption isotherm. It is based on the adsorption theory that was proposed by this persons, Brunauer-Emmett and Teller, in the year 1938. Therefore, it is known as the BET theory, Brunauer-Emmett-Teller theory. So, the adsorption isotherm that we are going to discuss, the BET adsorption isotherm, it is based on the adsorption theory that was proposed by Brunauer-Emmett and Teller in the year 1938. And this theory is known as the BET theory. The BET theory, it allows the formation of multiple layers of adsorbent molecules on different parts of the surface of adsorbent. So this is an improvement over the Langmuir adsorption isotherm, which allows only a monolayer on the adsorbent, on only a monolayer of adsorbent molecules on the surface of adsorbent. So that means you have the adsorbent surface, and the Langmuir adsorption isotherm was allowing only a monolayer of adsorbed molecules on the surface of the adsorbent. Whereas the BET theory, it allows formation of multiple layers on different parts of the adsorbent surface. That means the BET theory considers formation of multiple layers of adsorbent molecules. This was not the case with the Langmuir adsorption isotherm, which allowed only monolayer of the adsorbent molecules on the surface of the adsorbent. So this is the first thing that you have to note for the BET theory. The BET theory allows the formation of multiple layers of adsorbent molecules on different parts of the surface of the adsorbent. So those multiple layers could be formed on different parts on the surface of the adsorbent. So this is an improvement. We can say that this is an improvement over the Langmuir adsorption isotherm, which allows only a monolayer of adsorbent molecules on the surface of the adsorbent. Then like there were assumptions for the Langmuir adsorption isotherm. The Langmuir adsorption isotherm derivation of the equation, it was based on certain assumptions. Here also, the BET equations, the equation for BET adsorption isotherm, it is based on certain assumptions. What are these assumptions? Let us understand. No interaction between adjacent molecules on the surface of the adsorbent. That means once the molecules are adsorbed on the surface of the adsorbent, there is no interaction between this adsorbed molecules. That is the first assumption. No interaction between the adjacent molecules on the surface of the adsorbent. And then the second assumption is molecules adsorb at fixed sites and do not migrate over the surface. So once the molecules get adsorbed on the surface, the site remains fixed. The molecules will not migrate on the surface of the adsorb. This is the second assumption. Then the third assumption is the net empty space remains constant for the given equilibrium conditions. So once an equilibrium is reached, the net empty space on the surface of the adsorbent, it is not changing. This is an assumption. Then the fourth assumption is the surface occupied by the adsorbent molecules remain constant for the given equilibrium conditions. The surface that is occupied by the adsorbent molecules, it does not change under given equilibrium conditions. Once equilibrium is reached, the surface occupied by the adsorbent molecules, it remains constant, and even the empty surface on the adsorbent, it also remains constant under given equilibrium conditions. So that is the fourth assumption. So you have these four assumptions. The derivation of the applicable equation is based on this four assumption. No interaction between the adjacent molecules on the surface of the adsorbent, molecules adsorbed at fixed sites and do not migrate over the surface. The net empty space remains constant for the given equilibrium conditions. The surface occupied by the adsorbent molecules remain constant for the given equilibrium conditions. So based on this four assumptions, we will be deriving the equation that will be applicable for the BET adsorption isotherm, or we will be deriving the equation that will describe the BET adsorption isotherm. Okay, so to understand the theory, we will be considering adsorption of a component from a gas mixture. As you know, BET adsorption isotherm, it is applicable to adsorption of gases. So we are going to consider adsorption of a component from a gas mixture. The gas mixture, it has a high concentration of that component. So we are considering a gas mixture from which a component is getting adsorbed on the surface of the adsorbent, and concentration of that component in the gas mixture, it is high. So the gas mixture, it has a high concentration of that component. So we are considering a case of a gas mixture which has a high concentration of the component that is getting adsorbed. So for example, let us consider a gas mixture of A and B from which only A is adsorbed, whereas B is not adsorbed. And this gas mixture, it will be having a high concentration of A. So in other words, we are considering a gas mixture that has a high concentration of the component that will be adsorbed on the surface of the adsorbent. So specifically, we are considering a gas mixture of A and B. A is getting adsorbed, and concentration of A in the gas mixture is high. Now, there are two phenomena that happens in this case. So first is the creation of monolayers on the surface of the adsorbent. and the other one is loss of monolayer of the adsorbate molecules. Now let us understand how monolayer of adsorbate molecules is created on the surface of the adsorbent. So for that, let this be the adsorbent, and now it is contacted with the gas mixture of A and B. Now we know A is going to get adsorbed on it. So one way of creating the monolayer of adsorbate molecules on the surface of the adsorbent is this. How? The gas A or molecules of gas A gets adsorbed on the surface of the adsorbent and forms the monolayer. So that means monolayer, one of the ways of creating monolayer is adsorption on the empty surface. So you just had an empty surface, empty adsorbent surface, and now the molecules of gas A have adsorbed on the surface of the adsorbent, and in that process they have formed a monolayer. So this is one way in which monolayer is formed on the surface of the adsorbent. The other way is, let us say that you have this situation where there is a bilayer of adsorbent molecules, bilayer of A molecules on the surface of the adsorbent. Now, how monolayer will be formed out of this? Let us understand. So this will be formed when the bilayer, it gets dissolved from the surface of the adsorbent. So once the bilayer gets dissolved, you are left with the monolayer of gas A on the surface of the adsorbent. That means dissorption from the bilayer of the adsorbate molecules also results in the creation of monolayer of the adsorbate molecules on the surface of the adsorbent. That means there are two ways in which monolayers are created on the surface of the adsorbent. One way is by adsorption on the empty surface, and the other one is by desorption from the bilayer, of the adsorbate molecules. So I hope the concept is clear to you, how monolayer is created, or what are the two ways in which monolayer of adsorbate molecules is created on the surface of the adsorbent. So let us. Then the other phenomena that is involved, what is that? It is loss of monolayers. So now we understood how monolayer is created, and now let us understand how the monolayer that may be present or that is present on the surface of the adsorbent, it gets lost. Again, there are two ways in which this happens. So for understanding, I have considered two cases. So now we are going to understand how this monolayer will be lost from the surface of the adsorbent. First, so there will be desorption of the monolayer. So once the monolayer gets dissolved, the surface becomes empty. So monolayer is one way of losing the monolayer is by desorption of the monolayer. Whereas the other way is when few more adsorbate molecules, they get adsorbed on the surface of the adsorbent and forms the bilayer. So once you have the bilayer on the surface of the adsorbent, the monolayer is lost. So this is another way in which monolayer is lost. Adsorption of additional layers of the adsorbate molecules. So there are two ways in which monolayer can be lost. One is by desorption of the monolayer that was present on the surface of the adsorbent, and the second way is by adsorption of additional layers on the monolayer that is already present on the surface of the adsorbent. So I hope now you know how monolayer gets lost from the surface of the adsorbent. Now let us. So that means we have two processes. After looking at or after understanding how the process occurs, now we can note these points. We have the following two processes. One is creation of the monolayer and the other is loss of the monolayer. The monolayer is created in two ways. First is it is created by adsorption on the empty surface, and the second way is it is created by desorption from bilayers. Then the monolayer is lost again in two ways. One is it is lost due to desorption of the monolayer itself, and the second is it is lost due to adsorption of additional layers on the monolayer. So you have two processes: creation of the monolayer, loss of the monolayer. Monolayer is created in two ways: adsorption on the empty surface, desorption from the bilayer, whereas monolayer is lost in two ways: by desorption of the monolayer or by adsorption of additional layers on the monolayer. So the important point to note over here is a dynamic equilibrium is reached. A dynamic equilibrium for the monolayer is reached. And when this happens, when the rate of creation of the monolayer is equal to the rate of loss of the monolayer from the surface of the adsorbent. So when the rate of creation of the monolayer, again rate of creation is addition of rate of these two rates, rate of adsorption on the empty surface and rate of desorption from bilayers. So when these two rates are added, you get the net rate of monolayer creation. Similarly, when you add rate of desorption of the monolayer and rate of adsorption of additional layer, you get the rate of loss of monolayer. And a dynamic equilibrium for the monolayer is reached when rate of creation of the monolayer is equal to the rate of loss of the monolayer. So I hope the concept is clear to you. If you have any doubt, you please mention that in the comment section. And so let us now let us get the mathematical equations for creation of the monolayer. So first we will discuss creation of the monolayer by adsorption on the empty surface, the first way of creating monolayer. So in this case, the rate is proportional to the frequency at which adsorbate molecules strike the empty surface. So rate of adsorption on the empty surface, it is proportional to the frequency at which adsorbate molecule strikes the empty surface of the adsorbent, and it is also proportional to the area of this empty surface. That means the rate is proportional to two parameters. One is the frequency at which adsorbate molecule strikes the empty surface of the adsorbent, and the second is area of this surface. According to kinetic theory of gases, the striking frequency, the frequency at which adsorbate molecule strikes the surface, the striking frequency is proportional to the pressure of the molecules that are getting adsorbed. So you can understand it with the help of this schematic diagrams. So you have the adsorbent in contact with the gas mixture, and now the gas A is getting has adsorbed on the surface of the adsorbent by adsorbing on the surface. It has formed the monolayer. So if you have to represent it mathematically, RA naught, that is rate of adsorption on the empty surface, is directly proportional to A naught into PA. And if you remove the proportionality, it will be RA naught is equal to KA naught into A naught into PA. Let me call it as equation 1. In equation 1, A naught is the fraction of the empty surface available on the surface of the adsorbent. Ka naught is the velocity constant for adsorption, and Pa is partial pressure of A in the gas mixture. Okay. So the rate of creation of monolayer by adsorption on the empty surface is given by equation 1. It is Ra naught adsorption of A on the empty surface is equal to Ka naught into A naught into Pa, and we are calling this as equation number 1. Let us move ahead. Now, when the process continues, A is getting adsorbed on the surface of the adsorbent. So, as the concentration of A on the surface of the adsorbent increases, the adsorbed molecules, they act as hindrance to new adsorption, hindrance to the other molecules of A that are trying to adsorb on the surface of the adsorbent. So, as after this happens, after you have sufficient concentration on the surface of the adsorbent, the reverse process also starts. What is that reverse process? Some of the adsorbed molecules, they start getting desorbed. So, you have two processes. You have adsorption on the surface and then you have desorption from the surface. I have discussed this particular case in my earlier video, in my video on adsorption equilibria. You please watch it. Link to the entire playlist is available in the description section. So, you have adsorption, you have desorption, and now we will reach a dynamic equilibrium. So, at the dynamic equilibrium, a rate of adsorption will be equal to rate of desorption. Rate of adsorption will be equal to rate of desorption. Now, let us talk about rate of desorption. First thing is, you need to understand that desorption is an activated process, which means that the adsorbed molecules should possess certain minimum energy in order to get desorbed. So, that's why once the adsorbed molecules get that energy, which is called activated energy, they will be getting desorbed. So, that's why desorption is an activated process. And in this case, the rate of desorption is directly proportional to the fraction of the surface that is occupied by the monolayer. And you can represent it mathematically in this way. RD1 is directly proportional to A1. RD1 stands for rate of desorption of the monolayer. So, the number 1 in this case represents the monolayer. So, RD1 is directly proportional to A1. That is, RD1 is equal to KD1 into A1. So, in this case, A1 is fraction of the surface that is occupied by the monolayer of the adsorbate molecules, and KD1 is the velocity constant for desorption from the monolayer. So, 1 in this case stands for the monolayer. Then at dynamic equilibrium, what happens? Rate of adsorption on the empty surface becomes equal to rate of desorption from the monolayer. So, earlier we got equation for Ra naught, that was equation number 1. So, Ra naught is Ka naught into A naught into Pa. This is equation number 1 that we obtained previously. And now you have equation number 2, which gives us Rd1. So, Rd1 in this case is Kd1 into A1 into Kd1 into A1. And at equilibrium, A naught is equal to Rd1. That is Ka naught into A naught into Pa, that is equal to Kd1 into A1. And I am going to call this as equation number 3. So, when the monolayer is created by adsorption on the empty surface, you have this equation. You have rate of adsorption, you have rate of desorption, and then at the dynamic equilibrium, rate of adsorption on the empty surface will be equal to rate of desorption from the monolayer. And in that way, you get equation number 3, Ka naught into A naught into Pa, that is equal to Kd1 into A1. And I am calling this as equation number 3. Okay, so now let us understand creation of the monolayer by the other way. What is that? By a desorption from the bilayer. So when you have a bilayer on the surface of the adsorbent, the bilayer will get dissolved and there will be creation of monolayer on the surface of the adsorbent like this. So for this, the molecules from the bilayer which gets dissolved, they must possess certain activated energy. That's why desorption is an activated process, and the rate of desorption is then directly proportional to the fraction of the surface that is occupied by the bilayer. So in this case, the rate of desorption will be directly proportional to the fraction of the surface that is occupied by the bilayer. So mathematically, this will be RD2 proportional to A2. RD2 is rate of desorption from the bilayer, rate of desorption of the bilayer. It is directly proportional to A2. So that is RD2 is equal to KD2 into A2. And I am calling this as equation number 4. In this case, A2 is the fraction of the surface that is occupied by the bilayer of the adsorbate molecules, and KD2 is the velocity constant for the desorption of the bilayer. A2 is a fraction of the surface that is occupied by the bilayer, the adsorbate molecules. So the rate of creation of monolayer by desorption from the bilayer is given by equation number 4. Let us move ahead. Now we got a rate of creation for the monolayer by both the ways. Now let us get an equation for the net rate of creation of the monolayer. The net rate will be addition of the two rates. So the net rate is obtained by adding the rates of creation of monolayer by the two ways, that is by adsorption on the empty surface and then by desorption from the bilayer. So that is RNC. If the rate of creation of the monolayer is RNC, so RNC will be equal to RA0 plus RD2. Rate of adsorption on the empty surface plus rate of desorption from the bilayer. Then we have got equations for RA0 and RD2. RA0 is KA0 A0 into PA, whereas RD2 is KD2 into A2. And if you use these equations, you will get RNC is equal to KA0 into A0 into PA plus KD2 into A0, and let us call this as equation number 5. Now we are going to use equation 3 that we obtained earlier. What is that equation? KA0 is equal to A0, KA0 into A0 into PA is equal to KD1 into A1. That means in equation number 5, KA0 into A0 into PA will be replaced with this term. So if I use it in equation 5, RNC, the net rate of monolayer creation is equal to KD1 into A1 plus KD2 into A2. And now I am calling it as equation number 6. So equation 6 gives us the net rate of creation of monolayer on the surface of the adsorbent. Let us move ahead. So that ends our discussion for creation of the monolayer. Now let us talk about the other process. What is that process? Loss of monolayer. Again, it is going to happen in two ways. First way is by desorption of the monolayer. That is, when you have a monolayer of the adsorbent molecules on the surface of the adsorbent, and if this monolayer gets dissolved, the monolayer will be lost from the surface of the adsorbent. So this is desorption process. As I told you earlier, it is an activated process. The rate of desorption in this case is directly proportional to the fraction of the surface that is occupied by the monolayer. The fraction of the surface that is occupied by the monolayer will decide the rate. Actually, the rate is directly proportional to that fraction. So mathematically, this is RD1 directly proportional to A1. That is RD1 is equal to KT1 into A1. I'm calling it as equation number 7. In this case, A2 is a fraction of the surface that is occupied by the monolayer of the adsorbate molecules, and KD1 is the velocity constant for desorption of the monolayer, desorption from the monolayer. So equation 7 gives us the rate at which desorption of the monolayer takes place, which ultimately results in loss of the monolayer. So let us do it. Now, the other way of losing the monolayer, it is by adsorption of additional layers. So you have the monolayer on the surface of the adsorbent, and when there is adsorption of additional layers, for example, in this case, there is formation of bilayer. So monolayer is getting lost in this process. So in this case, you have adsorption, and the rate of adsorption in this case is proportional to the frequency at which the adsorbate molecules strike the monolayer on the surface of the adsorbent. So the frequency at which the molecules of gas A in the gas mixture will strike on the surface will decide the rate. So that's why the rate of adsorption, we are saying, is proportional to the frequency at which the adsorbate molecules strike the monolayer on the adsorbent surface. And the rate at the same time, it is proportional to the area of this surface on which monolayer is present. So mathematically, or before that, we know according to the kinetic theory of gases, this striking frequency, the frequency at which the adsorbate molecules strike the surface, the striking frequency is proportional to the pressure of the molecules. So mathematically, this will be expressed as RA1 proportional to A1 into P1. RA1 stands for rate of adsorption on the monolayer. And if you remove the proportionality, it will be RA1 is equal to K1 into A1 into PA. And now I'm calling it as equation number 8. So equation number 8 gives us the rate of loss of monolayer by adsorption of additional layers. So let us move ahead. Okay. In this, A1 is, the fraction of the empty surface that is available on the monolayer, because the rate will be proportional to that surface. And K1 is the velocity constant for adsorption on the monolayer, and PA is partial pressure of the gas E in the gas mixture. Equation 8 gives us rate of adsorption on the monolayer, which results in the loss of the monolayer that was originally present on the surface of the adsorbent. So let us move ahead. Now let us get the net rate. You have two processes for the loss of the monolayer, and the addition of rates of those two processes will give us the net rate for the loss of monolayer. So the net rate of loss of the monolayer is given by this equation RNL. RNL represents the net rate of loss of the monolayer. So that is equal to RD1 plus RA1. We got equation for RD1, it is KD1 into A1. And then we also got equation for RA1, which is KA1 into A1 into PA. So RNL will be equal to KD1 into A1 plus KA1 into A1 into PA. The net rate for loss of the monolayer. So now we got the net rate for monolayer creation, net rate for the loss of the monolayer. Now let us talk about the dynamic equilibrium. So at dynamic equilibrium, the net rate of creation of the monolayer is equal to the net rate of loss of the monolayer. RNC equation, we got equation for RNC, KD1 into A1 plus KD2 into A2, and now we got equation for RNL, which is KD1 into A1 plus KA1 into A1 into PA. And therefore, using these two in this equation, you get KD1 into A1 plus KD2 into A2, that is equal to KD1 into A1 plus KA1 into A1 into PA. And you can see KD1 into A1 is present on both the sides. So this term is going to get cancelled. This term is going to get cancelled. And you are left with KA1 into A1 into PA, that is equal to KD2 into A2. And I am calling it as equation number 9. Therefore, for the first layer that forms on the surface of the adsorbent, we have equation number 3, which we got earlier. What is that equation? Ka0 is equal Ka0 into A0 into Pa, that is equal to Kd1 into A1. So that means rate of adsorption on the empty surface is equal to rate of adsorption from the rate of desorption of the monolayer. Then for the second layer, which we have for the second layer, we have equation number 9. What is that equation? It is Ka1 into A1 into Pa, that is equal to Kd2 into A2. So according to this equation, rate of adsorption on the monolayer is equal to rate of desorption from the bilayer. So accordingly, we can write this type of equation for the remaining layers. So for example, similarly, for the third layer, you can easily understand this kind of equation will be written as Ka2 into A2 into Pa, that is equal to Kd3 into A3, where Ka2 into A2 into Pa gives the rate of adsorption on the bilayer, and Kd3 into A3 gives rate of desorption from the third layer, that's adsorbent molecules. So in general, if you have to write it for any ith layer, it will be written as written in this way: Ka for I minus 1 layer, A for I minus 1 layer into Pa. So that gives us rate of adsorption on on the I minus 1th layer, that is equal to Kdi into Ai, which gives us rate of desorption from the ith layer. So I hope you have understood how we get this equation. We are going to use this equation in our further analysis. Okay, so for the first layer, we get this equation. We have got this equation Ka0 into A0 into Pa, that is equal to Kd1 into A1. So from this I will write equation for A1, which is Ka0 upon Kd1. From this I will get equation for A1. So A1 will be equal to Ka0 upon Kd1 into Pa into A0. And in the next step I will replace this group Ka0 upon Kd1 into Pa with alpha naught. So that gives me this equation. A1 is equal to alpha naught into A0. And what is alpha naught? Alpha naught is Ka0 divided by Kd1 into Pa. Similarly, for the second layer, we have this equation Ka1 into A1 into Pa, that is equal to Kd2 into A2. And then we will get equation for A2, which is Ka1 upon Kd2 into A1 into Pa. And I'm going to call this as equation number 10. Now, according to the BET theory, according to the theory proposed by Brunauer-Emmett-Teller, after the first layer, this ratio remains constant. After the first layer, this ratio remains constant. Velocity constant of adsorption to velocity constant of desorption. The ratio of these two, it remains constant. that is Ka1 upon Kd2 is equal to Ka2 upon Kd3, that is equal to Ka3 upon Kd4. It remains constant, and we are going to denote that ratio by G, which is a constant. So for if I use it in equation number 10, equation 10 now will be written as A2 is equal to G into A1 into P. You must have understood Ka1 by Kd2 is now replaced with the constant G. So that gives me A2 is equal to beta into A1. And what is beta? Beta is G into Pa. So the product of G and Pa I am replacing with another parameter, that is beta. So A2 is equal to beta into A1. And so we can write similar equations for the remaining layers. So for other layers, for example, for the third layer, the equation will be written as A3 is equal to beta into A2. But A2, we have equation for A2, and if I replace that, it will be A3 into beta, and A2 is beta into A1. So it will be, I'm using that. So ultimately we get A3 as beta square into A1. Then for the fourth layer, we will have A4 is equal to beta into A3, and then I can replace A3 with this equation. So it will be A4 is equal to beta into beta square into A1. That is A4 is equal to beta cube into A1. So with this understanding, for any ith layer, we can write this equation. Er is equal to beta raised to I minus 1 into A1. So you can easily follow how we get this equation. Ai is equal to beta raised to I minus 1 into A1. And A1, we have got equation for A1 in terms of alpha naught into A naught. So A1 is alpha naught into A naught. So I can replace A1 with this. So that gives me Ai is equal to beta raised to I minus 1 into alpha naught into A naught. Then I can write this equation as beta I minus 1 is beta raised to I divided by beta. So beta raised to I into alpha naught upon beta into A naught. And in the next step, I will replace this ratio alpha naught by beta with capital P. So that gives me Ai is equal to capital B into beta raised to I into alpha naught. So in this case, capital B is alpha naught divided by beta. Okay, so I hope you have understood each and every step. If you have any doubt, you please mention that in the comment section. Let us move on. Now, since all small a's, that is A0, A1, A3, and for any nth layer, An, these are fractional areas. That means their summation, their addition will be equal to 1. So A0 and addition of all other a's, sum of all other a's will be equal to 1. Because sum of fractions is equal to 1. So A0 plus sum of all a's, summation of ai, where I goes from 1 to n, then it is equal to 1. But we got equation for ai previously. What is that equation? Ai is b into beta raised to I into A0. So I can use that equation. So I will get this. A0 plus summation from I is equal to 1 to n, b into beta raised to I into alpha naught, that is equal to 1. So I have replaced ai with equation for it. B into beta raised to I into alpha naught. Now the total volume of the gas that gets adsorbed, you can get it from this equation. V, which represents the total volume of the gas adsorbed, that is equal to V cap into summation from I is equal to 1, I is equal to 1 to I is equal to n, into I, the summation of this term I into AI. That is, you are adding the fractional areas for every layer and then multiplying with V cap to get the total volume of the gas adsorbed. What is V cap in this case? V cap in this case is the volume of the gas adsorbed on unit area of each layer. So V cap represents volume, or you can say V bar. V bar represents volume of the gas that is adsorbed on unit area of each layer. So you are multiplying the volume per unit area with the total area. So that gives us the total volume of the gas that is getting adsorbed on the surface of the adsorbent. So I hope this equation is clear to you. Now we will continue with this equation. So this is V upon V bar is equal to summation when I goes from 1 to I is equal to 1 to N, summation of I into AI, summation of I into AI when I goes from 1 to N, that is V upon V bar is equal to, I will just put it in a different form. V upon V bar is equal to summation of I into AI when I goes from 1 to N divided by 1. The denominator for this, the term on the right hand side of this equation is 1. And in the next step, I will be replacing 1 with this equation, because that is also equal to 1. So that is V upon V bar is equal to summation of I into AI where I goes from 1 to N divided by A naught plus summation of B into beta raised to I into A naught where I goes from 1 to N. But AI, we have equation for AI that we have obtained, and we are going to use that over here. AI is B into beta raised to I into A naught. So that gives us V upon V bar is equal to summation of I into beta, I into B into beta raised to I into A naught when I goes from 1 to N divided by A naught plus summation of B into beta raised to I into A naught when I goes from 1 to N. So in this way we get an equation for V upon V bar. We are going to continue with this equation. Okay, so the equation that we obtained previously, I am calling it as equation 11. And what is that equation? V upon V bar is equal to summation of I into B into beta raised to I into A naught when I goes from 1 to N divided by A naught plus summation of B beta raised to I into A naught when I goes from 1 to N. Now, B and A naught, they are not involved in the summation, so they can be taken out in the numerator. So it will be V upon V cap is equal to B into A naught into summation of I into B raised to I, where I goes from 1 to N, divided by A naught plus B into A naught summation of beta raised to I when I goes from 1 to N. And I am calling this as equation number 12. I am calling this as equation number 12. Now for flat unrestricted surface, when you have flat unrestricted surface of the adsorbent, there is no theoretical limit on theoretical limit of layers that can build up. What is the meaning? Infinite layers can be formed on the surface of the adsorbent if you have unrestricted surface, unrestricted flat surface. When the surface is flat and there are no any restrictions for the adsorption, so there in that case there is no theoretical limit on the formation of layers. That is, infinite number of layers can be formed on the surface of the adsorbent. So that is we can replace n in equation 12 with infinity. So if you use that, we'll have v upon v bar is equal to b into a naught summation of I into beta raised to I, where I goes from 1 to infinity, divided by a naught plus b into a naught into summation of beta raised to I, where I goes from 1 to infinity, and I'm calling this as equation number 30. Now we will simplify the numerator and denominator of equation 30. Starting with the numerator. What is the numerator? Numerator is b into a naught into summation of I into beta raised to I, where I goes from 1 to infinity. So that is b into a naught into beta, 1 into beta plus 2 into beta square plus 3 into beta cube plus dash dash dash, where I is infinity. You have infinite terms in this series. So that is b into a naught into summation of I into beta raised to I, where I goes from 1 to infinity, is equal to beta b into a naught into beta. So from each term I am taking beta common. So if I do that, what is left in the bracket? It will be 1 plus 2 beta plus 3 beta squared plus 4 beta cubes, so on and so forth. And I'm calling this as equation number 40. Now we know that the summation, you have summation of beta I, where I goes from 1 to infinity, is beta plus beta square plus beta cube plus so on and so forth. Now if I differentiate this summation, so that is d, we differentiate with respect to beta. So d by d beta of summation beta raised to I, where I goes from 1 to infinity. That means differentiation of the term on the other side, that is d by d beta of beta plus beta square plus beta cube plus dash dash dash. Okay, so in the next step we are going to see what would be the differentiation, how we can use it in our further analysis. Okay, so we have equation 13, which is v upon v bar, that is equal to b into a naught summation of I into beta raised to I, where I goes from 1 to infinity, divided by a naught plus b into a naught summation of beta raised to I, where I goes from 1 to infinity. We were analyzing this equation. We were analyzing the equation and we had started with its numerator. The numerator in equation 13 is b into a naught into summation I beta raised to I, where I goes from 1 to infinity, and we had got equation 14 earlier. Equation 14 was obtained previously, and we were differentiating this summation. D by d beta of the summation is equal to d by d beta of this series. So if you differentiate with respect to beta, what are you going to get? D by d beta of summation beta raised to I, from where I goes from 1 to infinity, will be 1 plus 2 beta plus 3 beta square, and similar terms will continue further. That means if you look at equation 14, you have a term like this in equation 14. So our next job is to replace this term with this differentiation. So if you use it in equation 14, it will be b into a naught of b into a naught into summation of I beta raised to I, where I goes from 1 to infinity. That will be equal to b into a naught into beta. And now this series we are replacing with the differential term that we have got. So this is d by d beta of summation of beta raised to I, where I goes from 1 to infinity. Okay, so we were analyzing equation 13. The numerator is b into a naught. For the numerator, we got this term previously. Now the series on the right hand side, that is summation of beta raised to I, where I goes from 1 to infinity, is beta plus beta squared plus beta cube, and so forth. So this is nothing but infinite geometric progression, and you have one formula for that. What is that formula? Summation where I goes from 1 to infinity of beta I is beta upon 1 minus beta. Therefore, if you use it, you'll get b into a naught into summation of I beta raised to I, where I goes from 1 to infinity, that is equal to b into a naught into beta into d by d beta of beta upon 1 minus beta. That is b into a naught into summation of I beta raised to I, where I goes from 1 to infinity, that is equal to b into a naught into beta. And now I'm differentiating it. So I'm using the product rule. This is beta into 1 upon 1 minus beta. So beta into differentiation of the other term, that is 1 upon 1 minus beta, it is minus 1 upon 1 minus beta square, into differentiation of the function in the denominator, which is 1 minus beta, and differentiation of that is minus 1, plus the other term now it is kept constant, 1 upon 1 minus beta, and differentiation of beta is 1. So you get this equation. That is b into a naught into summation of I beta raised to I, where I goes from 1 to infinity, that will be equal to b into a naught into beta into, and this becomes beta upon 1 minus beta square plus 1 upon 1 minus beta. Then I will make the denominator same for both the terms. So it will be b into a naught or into summation of I beta raised to I, where I goes from 1 to infinity, that is equal to b into a naught into beta divided by beta upon 1 minus beta square plus 1 minus beta upon 1 minus beta square. So I hope you are following me. If you have any doubts, you please mention them in the comment section. Let us move ahead. Now the numerator is transformed to this form, b into a naught into summation I beta raised to I goes from 1 to infinity, that is equal to b into a naught into beta upon 1 minus beta square plus 1 minus beta upon 1 minus beta square, that is b into a naught into summation I beta raised to I, where I goes from 1 to infinity, that is equal to b into a naught into beta, and now you have beta plus 1 minus beta divided by 1 minus beta square, that is b into a naught into summation I goes from 1 to infinity, summation of I beta raised to I, where I goes from 1 to infinity, that is equal to b a naught into beta, and beta minus beta becomes 0, so you will have this term 1 upon 1 minus beta squared. So that is b into a naught into summation of I beta raised to I, where I goes from 1 to infinity, is simply equal to b into a naught into b upon 1 minus beta squared. So now let us, that is how we simplify the term in the numerator of this equation. Now let us look at the denominator. In the denominator you have this series, summation beta raised to I, where I goes from 1 to infinity, which is nothing but beta plus beta square plus beta cube plus beta raised to 4, so and so forth. That is summation of beta raised to I. We have formula about this. Summation of beta raised to I, where I goes from 1 to infinity, is beta upon 1 minus beta, the infinite geometric series. So in the next step we will replace the summation term in the denominator of this equation. So let us move ahead. So the numerator now we got simplified, b into a naught into summation of I beta raised to I, where I goes from 1 to infinity, now is b into a naught into beta upon 1 minus beta square. In the denominator, the series summation is summation of beta raised to I, where I goes from 1 to infinity, is nothing but beta upon 1 minus beta. Now let us use these terms in equation 13. So now equation 13 will be b upon v bar is equal to b into a naught into beta upon 1 minus beta square. We have replaced with the simplified term, and in the denominator the summation is replaced with the simplified term. So b into a naught into beta upon 1 minus beta square divided by a naught plus b into a naught into beta upon 1 minus beta. That is v upon v bar. We will simplify it further. So this is b into a naught upon beta divided b into a naught into beta divided by 1 minus beta square, and in the denominator you have a naught into 1 minus beta plus b into a naught into beta divided by 1 minus beta. I have simplified it. So that is v upon v bar will be equal to b into a naught into beta divided by so 1 minus beta gets cancelled with this, and then after simplification you get this equation. V upon v bar is equal to beta into a naught upon beta divided by 1 minus beta into a naught into 1 minus beta plus b into a naught into beta. In the next term, in the next step, what we will do, we can take a naught common in the denominator. So it will be v upon v bar is equal to b into a naught into beta divided by 1 minus beta into a naught, and in the bracket it will be 1 minus beta plus b into beta. Let us continue with this. So previously we got v upon v bar is equal to b into a naught into beta divided by 1 minus beta into a naught into 1 minus beta plus b into beta naught. Now I'll just rearrange this equation. So first what I will do, okay, a naught in the numerator and in the denominator it is cancelled out. So now you have v upon e bar is equal to b into beta divided by 1 minus beta into 1 minus beta plus b into beta. I'm calling it as equation 15. Now when PA is increased to PA naught, what is PA? PA is partial pressure of A in the gas mixture. When PA, you increase PA to PA naught. What is PA naught? PA naught is the saturated vapor pressure. So if you do that, that is if PA is equal to PA naught, condensation of the gas will occur. Condensation and not adsorption when PA becomes equal to PA naught. When PA becomes equal to PA naught, condensation occurs on the solid surface. And in that case, V upon V infinity, V upon V bar, it becomes infinite. V upon V bar, it becomes infinite when P becomes equal to the saturated vapor pressure. And according to equation 15, if V upon V bar is infinite, that means beta is 1. If you put beta is equal to 1 in this equation, then and then only you'll get V upon V bar is equal to infinity. We had earlier defined beta as G into PA. And when PA is equal to PA naught, beta is equal to 1. We have understood this. So that means 1 will be equal to G into PA naught. That is G will be equal to 1 upon PA naught. So now I can replace this equation for G in the definition of beta. So using in the definition of beta, you have beta is equal to PA upon P naught. Okay, so equation 15, we got previously V upon V bar is equal to B into beta divided by 1 minus beta into 1 minus beta plus B into beta. So now I will rearrange it. So I'll take V bar on the other side. So V will be equal to beta. We also got an equation for beta when P becomes equal to PA naught. So we are going to use that. First, let us rearrange the equation. So V is equal to B into beta into B bar divided by 1 minus beta into 1 minus beta plus B into beta. Further rearrangement gives this equation. So I am taking this term to this side, B to the other side, and B into V cap on V bar on the left hand side. So this is 1 minus beta plus B into beta divided by B into V bar, that is equal to beta upon 1 minus beta into V. In the next step, again what we will do, this is that is I have written it in a different form. I have I'm writing the same equation, beta upon 1 minus beta into V, that is equal to 1 minus beta plus B into beta upon B into V bar. That is beta upon 1 minus beta into V is equal to, now from these two terms I have taken beta common, so it will be 1 plus beta into B minus 1 upon B into V bar. That is beta upon 1 minus beta in beta upon 1 minus beta into V. Now I am separating the denominator, so it is 1 upon B into V bar plus beta into B minus 1 divided by B into V bar. That is beta upon 1 minus beta into V is equal to B minus 1 upon B into V bar into beta plus 1 upon B into V bar. I have rewritten the equation. Now let us replace beta with PA by PA naught. How we got this? I have discussed it previously. So the equation will be PA by PA naught divided by 1 minus PA by PA naught into V, that is equal to B minus 1 upon B into V bar into PA by PA naught plus 1 upon V into V bar. And now I'm calling it as equation number 6. So what we have done, we have replaced beta with PA by PA naught. Let us continue further. Okay, so we obtained equation 16, which is PA upon PA naught divided by 1 minus PA upon PA naught into V, that is equal to B minus 1 upon B into V bar into PA by PA naught plus 1 upon B into V bar. Now this equation, it is of this form, y is equal to mx plus c, where y is this term, PA by PA naught divided by 1 minus PA upon PA naught into V, x is PA upon PA naught, and then m is B minus 1 upon B into V bar, and c is 1 upon B into V bar. So this, you know, this is equation of a straight line. This is equation of a straight line which has a slope of m and intercept on the y-axis is c. And for this equation, now you know what is y, what is x, what is m, and what is c. So let us you can plot it. So when you plot y on the y-axis, x on the x-axis, you'll be getting a straight line which will be having a slope of m and which will make an intercept of c on the y-axis. So PA by PA naught, it is plotted on the x-axis because x is PA by PA naught, and then PA by PA naught divided by 1 minus PA by PA naught into V, it is plotted on the y-axis because it is y. Let me erase it. So you'll be getting a straight line which has a slope of B minus 1 divided by B into V bar, and which makes an intercept on the y-axis. And what is that? What is the intercept? It is 1 upon B into V bar. So equation number 16 is the equation for the BET adsorption isotherm. This is the equation for the BET adsorption isotherm. And now you know how to get the values of B and V bar. So you can get those values from the slope of the line, slope of this line, and the intercept made by the line on the y-axis. So in this way, we get the equation for the BET adsorption isotherm. This equation, equation 16, PA upon PA naught into 1 minus PA upon PA naught into V is equal to B minus 1 divided by B into V bar into PA upon PA naught plus 1 upon P into V bar is the equation for the BET adsorption isotherm. And now you know how to plot that equation. Let us move further. Okay, now let us go back to equation 12. What is that equation? V upon V bar is equal to B into A naught into summation of I into beta raised to I, where I goes from 1 to n, divided by A naught plus B into A naught, summation of beta raised to I, where I goes from 1 to n. So, if you remember, in our previous analysis, we had replaced n with infinity. That is, infinite number of layers of the adsorbed molecules were allowed to form. And that was according to the BET theory. Now, if n is equal to 1, that means only one layer is allowed to form on the surface of the adsorbent. That is, when there is only formation of monolayer, then it will be this equation should get transformed to the equation for the Langmuir adsorption isotherm. So that is when n is equal to 1, adsorption is confined to a monolayer, and by putting n is equal to 1 in equation number 12, we can get equation for the Langmuir adsorption isotherm. So let us do that. So you have V upon V bar is equal to B into A naught into summation of I beta raised to I, where I goes from 1 to 1, divided by A naught plus B into A naught, summation of beta raised to I, where I goes from 1 to 1, and that is simply V upon V bar is equal to B into A naught into beta, divided by A naught plus B into A naught into beta. Now A naught is common, that gets cancelled out. So it will be V upon V bar is equal to B into beta upon 1 plus B into beta. I will rearrange it, 1 plus B into beta into V, that is equal to beta into B into V bar. Further rearrangement gives us V plus B into beta into V, that is equal to B into beta into B into V bar. But in this case, beta is, we have got equation for beta. Beta is Pa upon Pa naught. So if I replace it, it will be V plus B into V into Pa upon Pa naught. That is equal to Pa upon Pa naught into B into V cap. And now I will divide each term in this equation with this product B into V into V bar. So that will give me 1 upon B into V bar plus 1 upon V bar into Pa upon Pa naught, that is equal to Pa upon Pa naught into 1 upon V. And then I can rearrange it in this way, Pa upon Pa naught into 1 upon V, that is equal to 1 upon V bar into Pa upon Pa naught plus 1 upon V into V bar. So this equation is equation for the Langmuir adsorption isotherm, and you can plot it. So if you plot this term on the y-axis and this term on the x-axis, you are going to get a straight line which will be having a slope of 1 upon V bar and an intercept of 1 upon B into V bar. So in this way, when you keep n is equal to 1 in this equation, the equation gets transformed to the Langmuir adsorption isotherm. So with this, I end my discussion for the BET adsorption isotherm, Brunauer-Emmett-Teller adsorption isotherm. I have told you how to get the equation for the adsorption isotherm, for the BET adsorption isotherm, and then how from this equation for this you can get equation for the Langmuir adsorption isotherm. So I hope you have understood the derivation. If you have any doubts, you please mention them in the comment section. Thanks for watching this video. Do subscribe to my channel, tell your friends to subscribe to it, and hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, have a nice day and hope to see you soon in my next video. Bye.